Hey everyone, there you are. All right, so I changed the angle a little bit. I'm sitting down again. Sometimes I stand up, sometimes I sit down. Now I'm sitting down. I redid my desk a little bit. So now you know. All right, let's get to it. Now we are going to do two new types of approximations. We did left-hand Riemann sums and right-hand Riemann sums, which were cool for approximating. There are two better ones though. One is called a trapezoidal and one is called the midpoint. So let's do both. Two examples, just like before. Let's start with the basic x squared, I guess. X squared. Let's do the interval from 0 to 6 for both. All right, so I'm going to do a trapezoidal using, let's do 3 subintervals. Trap with 3 subintervals. All right, let's do a quick sketch, just like yesterday or 2 days ago. Looks like this. X squared is there. I don't really mind what it looks like. So 3 subintervals. So here's 2. Here's 2, 4, and 6. So again, we're dividing it into even or equal subintervals. So if I'm dividing it into 3, 2, 4, and 6 will do the trick. So one of them's going to be there. One of them's going to be there. Same as a left hand and a right hand, believe it or not. So these actually are going to look similar. Watch this. Don't write it down because I'm going to just show it to you. A left hand goes like this. Ready? It starts from the left point and goes left to right. If you'll notice, this counts as no rectangle. Sometimes that happens. Sometimes your left to right, or sometimes your right to left, is not going to even have a height to it. It would just be 0. Yep, it's fine. And then go left to right, and then go left to right. And the left-hand Riemann sum looks like this. Okay, it'd be 0 plus this area plus this area. Okay, that's a left-hand Riemann sum. We're not doing a left hand. Right hand goes this way. Ready? Way over, way over, way over. Over approximation. Okay. Let's talk about what a trapezoidal one is, though. Here's what a trapezoidal is. You're basically making trapezoids. Trapezoids. What is a trapezoid? Typically, a trapezoid looks like this. Wow. A trapezoid looks something like that, where these two sides are parallel, and then it's not, this side, the left side and the right side don't have to be equal to each other, but these two are parallel. That's the important part. One of the things you're going to have to know how to do is find the area of a trapezoid. Before we get into this, how do you find the area of a trapezoid? Well, if this is the height, the area of the trapezoid, let's call this base 1 and base 2. What's the area of a rectangle? Length times width, right? Turns out a trapezoid is actually very similar. Rather than do the base times the height, it is kind of the base. It's actually an average of the two bases. So you do base 1 plus base 2 divided by 2. You average the bases together times the height. So really, it's not that complex. It's just, rather than do a base times height, you're like, oh, I have 2 bases. Let's just average them together. That's what an average is when you add them up and divide by 2. That's the area of a trapezoid. Typically, we write it like this, though. 1/2 height base 1 plus base 2. Typically, that's how you're going to see it. Okay, so how does that apply here? We're going to make 3 trapezoids. Ready? I'm going to do from 4 to 6 first. Connect that point to that point. Connect this point to this point. That's a trapezoid. I'm actually going to turn it sideways so you can see it. So it looks like this. One interesting thing is, if you notice, this side right here is not slanted. It's straight up and down. Is it still a trapezoid? Yeah, it's still a trapezoid. It's actually even better because we know this distance right here is going to be the height. So what is this distance, the height? That's literally that distance right there. It's our base length. So the base from earlier when we were doing Riemann sums is the height of these trapezoids. How convenient. What are these two values? What is this value down here? This value is this value. That's f of 6. What's this value up here? This value is right here, f of 4. Plug them in and you're set. So the area of this guy is going to be 1/2 the height, which in this case is 2, times base 1, top base, which is f of 4, plus f of 6. That's how you're going to find the area of each of these trapezoids, which is 1/2 times 2 times what I get when I plug in 4, which is 16, because 4 squared is 16, and 6 squared is 36, which is 16 plus 36, 42, 52. So this one was 52. Keep going. Okay, so that was one of them. Let's talk about this one. You don't really have to draw that once you know what you're doing. It's 1/2. The base is not going to change in these ones. Down the road it is. I'm not going to worry about that right now. For today, the base is going to be the same every time because we're creating equal size or equal height trapezoids. And in this case, the base one is f of 2 plus f of 4. F of 2 is this distance. F of 4 is this distance. Add them up. F of 2 is 4 plus f of 4 is 16. Looks like we get 20. So this guy is 20. And this one is 1/2 to f of 0 plus f of 2. Well, f of 0 is 0. Is that a problem? Nope. You just include it. F of 2 is 4, like we said. So this cool area right here is 4. Add them all up. And that's our trapezoidal approximation. That looks like 4 plus 20 is 24, 76. And hopefully I didn't mess this one up like I did the other day. That's a trapezoidal approximation. You basically are just connecting point to point, and you're making an approximation. Let me really accentuate this graph. If you have a super concave up graph, and I connect this point to this point, or if I have a concave up decreasing graph and I do a trapezoidal, what do you think? Trapezoidal over approximation or an under approximation? I kind of didn't do it service in this picture, which is why I did it more over here. Turns out the trapezoidal in this case is going to be an over approximation because the function is concave up. So if you really thought about like, okay, what if the parabola looked like this? If it's concave up, trapezoid is an over approximation. We're getting all of this so our trapezoid would look like this. We're including extra area. It doesn't even matter if it's increasing or decreasing. If trapezoidal, if it's concave up, trapezoidal is an over approximation. Which means, sorry, I ran out of room. If it's concave down, as we'll see in a sec, concave down, well, you could draw it. Here's a concave down increasing, here's a concave down decreasing. What happens? If you connect these two dots straight away, check it out, you're missing out on area. Same thing in this one. If I connect these two and thought about how the approximation would work, I'm missing out on area. So this is an under approximation. Okay. So Riemann sums, when you're doing a left or right, it deals with increasing or decreasing. If it's trapezoidal or midpoint, you got to look at the concavity. All right. So I think that's pretty straightforward, more or less. We'll practice that too. How does midpoint work? Same problem. Let's do 3 subintervals with the midpoint. So B, same function. Let's do a midpoint with 3 subintervals. So now we're doing a midpoint Riemann sum. So it's still going to be rectangles. At the end of the day, we're still doing rectangles. Here's how this one works. Midpoint's one of the cool ones because, well, it's cool if you don't have a table. We're going to get to some of these where you have a table and then midpoint doesn't work so well. But midpoint's pretty cool because here's how it works. Let's call that 6. Let's call this 2 and 4. Our lovely sketches. Fine. 4, 2. Good enough. I know it's a little off. It's fine. Okay. So again, go here. Let's change the color. We're doing 3 subintervals. So 1, 2, 3. Left hand, we do left to right. Right hand, we do right to left. Trapezoid, we connect the endpoints and use the area of a trapezoid. What does midpoint do? Here's what midpoint says. If this is my first rectangle, and the bases from 0 to 2 go halfway between 0 and 2. So right here at 1, and make that the height of your rectangle. If you have 2 to 4, go halfway between, go up, and make that the height of your rectangle. If you're going from 4 to 6, go halfway between 5, and make that the height of your rectangle. Okay? Why is that so cool? Well, check it out. You're missing out on area. In this case, I guess you're missing this area. But you're adding area. Are they the same? No, but they're pretty darn close. Turns out the more concave up or down this is, the worse it is. But if it's not super concave up or down, it's actually not that bad. So you're missing this area, but you're counting extra area. Or I should say it the other way. You're counting extra area, but you're missing out on this area. You're counting this extra area, but you're missing this area. That's the cool thing about the midpoint. It is kind of it's not an average of left and right, turns out. It is a cool way to kind of account for extra and get rid of some. So the area of these three, again, this is not so bad. You just got to think, how did you get the height of this? It's the base 2 times the height. And what's the height of this? Well, it's this guy. It was f of 5. So it's between 4 and 6. This one is 2 times f of 3. This one is 2 times f of 1. So this is 2. This is 2 times 9, which is 18. This is 2 times 25, which is 50. Add them up. Looks like we get 70. How did that compare to the trapezoid? Trapezoid was 76. The midpoint's 70. Pretty close. And we said that the trapezoid is an over approximation. Any guesses on what the midpoint is? Turns out if it's concave up and the trapezoid is an over, the midpoint is an under. So they're always opposites. Midpoint is under. Midpoint is an under approximation. Trapezoid is over. So same thing, if it's concave up or concave down, then the midpoint is an under. Yeah, you can try to memorize all these. I think it's better to just think about, like I said, these pictures. Like actually sit there and think, okay, if the graph is concave up, what does a trapezoid look like? And then at that point, you don't have to necessarily think about a midpoint, why it's an over under, but if you check it out, because it's concave up, you're counting all this area. Well, the graph is not good to look at because it's not to scale. Just trust me. Okay, it's the opposite of the trapezoid. If I had a more to scale graph, you would see that you're missing out on. If it's concave up like this, the midpoint is under because you are missing out on more area than you're counting. Yes, just start to remember these rules. All right, let's do one more example. Where we at? 13 minutes, not too bad. That's the idea. So if you think you got it, great. Let's do one more. I'll try to do it all on one graph. Let's say find the area under this function, -1/2 x squared plus 4 from 0 to 2. Let's do a trap with 2 subintervals. And let's do a midpoint with 4 subintervals. That will be annoying. Okay, but this will be a good practice. Yeah, it's fine. All right, let's do it. So sketch it. What does -1/2 x squared look like? It kind of does this. And at 2, if I plug in 2, I get 2 squared, which is 4, divided by 2 is -2 plus 4 is 2, so technically I'm still not there. So let's just say it's right there. All right, so these are my 2 subintervals. We'll call this 1 and 2. So the trapezoid, let's do that one first. It is 1/2. So I'm going to do this trapezoid first. Connect this dot to this dot. 1/2, base 1, which is, let's do the height first. The height, which is, in this case, 1. Times base 1, which is this distance, which is f of 0, plus base 1, or base 2, which is this distance, f of 1. And then we'll come back to that. Let's do this next one real quick. It is 1/2 1 times f of 1 plus f of 2. Now I can plug everything in. That would be 1/2 f of 0. When I plug in 0, I get 4. When I plug in 1, I get 3.5. That's annoying. Great. When I plug in 1, I get, again, 3.5. Plus, when I plug in 2, I get 2 squared is 4, divided by 2 is 2, negative 2, negative 2 plus 4 is 2. So add these two up, and that will give me my approximation, half of 7.5 and half of 5.5. And I'm just struggling not to want to get Desmos out, which I won't. What is this? 3.75 plus half of 5.5 is 2.75, which is 6.5. Or I could have been way smarter and added 7.5 and 5.5, which is 13, and then divided by 2, which is 6.5. Why am I doing this? Because on the AP test in years past, they actually expect you to be able to add decimals and fractions without a calculator. There are non-calculator sections, so why should I be lazy when you're going to be required to do it soon enough? So if we were in class, you would have to do this a lot more. We lost that this year, sadly. All right, let's do the other one, midpoint with 4 subintervals. Okay, watch how this one's going to get a little obnoxious, and I may just bust out my calculator. So I'm going to come back to the graph, and I'm really going to show you what each of these looks like. Ready? So if I'm doing 4 subintervals, that means I have to draw 4 rectangles. So that means this is going to be 1, and this is going to be 1. Okay, so how am I going to get the area of each of these rectangles? How am I going to get the height? Halfway. So remember, this is 0.5, and this is 1.5. Halfway between 0.5 and 0, that's going to be the height I use. So in this first case, I'm going to treat it very carefully. It is the base length, which is definitely a half, or 0.5, times, well, how did I get the height of this? It's not f of 0, it's not f of 0.5. It's between those two. It is f of 0.25. Plus, the next one is f of, how do I get the area of the next one? Base is still 1/2, but the height, what do I get? It's 0.75. Halfway between 0.5 and 1. Next one, halfway between 1 and 1.5, hopefully you're catching on, would be f of 1.25. And then the last one would be f of 1.75. Cool, because halfway between 1.5 and 2 would be 1.75, and I got to plug that in. All right, so at this point, now you can join me in being lazy and finishing this one strong. Come on. Here we go. Let's do Desmos. Stop it. Stop it. There we go. Let's learn together. Let's do it. What happened to my whiteboard? There it is. Okay. What am I doing? Oh yeah, so I did negative 1/2 x squared. So remember, I do like showing you this again and again because getting used to Desmos and calling up the functions you're storing is crucial, especially when we do it with graphing calculators if we have to, but Desmos makes it really easy. So what am I doing? It's 1/2 times, and since I'm doing it to all of them, I can just literally like think about it as distributing out a 1/2, and I'm just adding all these up. F of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. 6.6875. What did I get in my earlier approximation? 6.5. Wow. So, pretty good. What's the real answer? How would I find the exact area under the curve? We'll never know. Or we'll know next class. Or or some of you already know because you did my discussion and I gave it away. But if you think you know, you can try your logic and test it. All right. Last thing I'm going to do, since we do have a little bit more time, let's do a really easy AP problem because I'm feeling in the mood. Try something sketch. New. Where does the following function have a local? All right. Anytime you want to do practice, you can literally just go to Google and type in AP Calc AB practice problems. And there are lots. So here's one. I don't think this is particularly hard, but maybe you forgot how to do this. Where does this function have a local max? I don't use the word local. I use the word relative, not absolute. A lot of times we'll actually have to find absolute max. It's more interesting, but I'd have to give you an interval. But in this case, relative max. Relative maximum means where the derivative equals 0 and it's a max. So let's take the derivative, set it equal to 0, find the critical points, and then test it. So take the derivative, 3x squared minus 27. Probably going to factor that. So equals 3 times x squared minus 9. 3 times x plus 3 times x minus 3. Good old difference of squares. 2 critical points. 3, negative 3. Negative 3, 3. Let's test them. If I plug in a million, it's positive increasing. If I plug in 0, that's negative decreasing. If I plug in negative a million, I'm squaring that, so it's increasing. So where's the local max? Right there, negative 3. Or if you were feeling really cool, you could have done second derivative tests. So once you got here, second derivative test says take the derivative, which is 6x. Plug in negative 3, you get concave down, right? F double prime of negative 3 is equal to a negative, which means concave down, which means it has to be the relative max. You remember that one? No? It's okay. We'll go back to all of these little tricks. But if you remember, that's called the second derivative test, where you put your critical point into the second derivative and see if it's a positive or negative. I think the first derivative test is faster, especially you already have them. This involves finding another derivative, and you'd have to test both, which just happens we got lucky the first time. All right, so that's it. Good luck with the homework. Riemann sums and area approximations are pretty much over. We're going to get into some real stuff very soon.